matrix decompositions, eigenvalues, and numerical ranges. 100 BCE, people are interested in solving practical problems, like the one written in chapter 8 of the 9 chapters on the mathematical art, an ancient Chinese text. The problem goes as follows. 3 sheaves of a good crop, 2 sheaves of a mediocre crop, and 1 sheaf of a bad crop are sold for 39 dough, a currency. 2 sheaves of good, 3 mediocre, and 1 bad are sold for 34 dough. 1 good, 2 mediocre, and 3 bad are sold for 26. The question then is, what's the price for a good crop, for a mediocre crop, for a bad crop? We can translate this problem into a problem of finding values. Next slide. G, M, and B that simultaneously satisfy 3 equations. In matrix language, we can write this as a matrix like the following. Identify the coefficients that appear on the left side of the equation and place them on this side of the matrix. And we identify the numbers on the right and place them on this side of the matrix. Hence, the system of 3 equations and 3 unknowns is now represented as a single matrix equation, AX equals B, where A is the matrix on the blue rectangle and B is the matrix on the red rectangle. In general, matrices are simply array of numbers. Matrices come up in areas where information have to be arranged in an orderly manner. Here we see the use of matrices in encoding information about this system of 3 equations in 3 unknowns. Matrix theory is the study of matrices and their properties. The remarkable insight that matrix theory has is that problems like this system of equations, can be solved by just studying matrices themselves. Under certain conditions, matrices can be added or multiplied. So for instance, we have this matrix A. We can write this as the product of 2 matrices, L and U, defined on the slide. What I would like to point out is the matrix L has this interesting property that above this diagonal, all entries are 0. In this case, we say that the matrix L is lower triangular. On the other hand, the matrix U has this property that all entries below the main diagonal are all 0. In this case, we say that U is upper triangular. This example illustrates an area of matrix theory called matrix decompositions, where we write matrices in terms of other matrices with special properties. Slide shows in particular LU factorization of matrices, where we try to write the matrix as a product of a lower triangular matrix L and an upper triangular matrix U. All right, so what about this LU factorization? What's the deal with it? Is it merely like a mathematical curiosity? Well, turns out solving the linear system AX equals B is equivalent to solving 2 linear systems involving L and U. Okay, that might sound like we're making the original problem more complicated by introducing 2 more problems. But believe me when I say that solving these 2 new problems are actually much easier, which I'm going to show and illustrate in an example. Consider the discretization of this boundary value problem, which is widely used. The discretization leads to solving a linear system AX equals B, where the matrix A is this matrix. Let's solve this system in 2 ways. Let's solve it using the LU. If the size of that matrix A is 500 by 500, very modest size, the time it takes for LU to solve the problem, it's about 0.0098 seconds. The time it takes to solve the system using the inverse, it's about 0.083 seconds. This might not seem like a lot of difference, but in the discretization problem earlier, ideally, we would like the matrix to be very big. So let's say we bump up the size to 10,000 by 10,000. Well, the time it takes for LU to solve the problem is about 22 seconds. But the time it takes for the inverse to solve the problem, 331 seconds. This drastic time difference can also be seen in this graph. The red asterisks correspond to the time it takes for the inverse to solve the problem, while the blue asterisks, mostly at the bottom part of the graph, represent the time when we use the LU factorization for differently sized matrices. Here's a photo taken last September in Germany. Yours truly and Neil Dizon, also a graduate from the Institute of Mathematics. Neil and I attended the Heidelberg Laureate Forum, and we were part of the 200 researchers in mathematics and computer science from all over the world who were invited to participate in this conference. And we were the only Filipinos last year. What I would like to point out though is, I hope you agree with me that these two photos look identical, right? But they're actually two different photos. To explain it, we need to discuss the next matrix decomposition called the singular value decomposition. Here, we now write the matrix as a product of three matrices with special properties. In particular, the one in the middle, sigma, is a diagonal matrix whose entries on that diagonal are all non-negative. Let's denote them by sigma 1 to sigma r. These are non-negative numbers. They are referred to as the singular values of the matrix A. If we disregard some of these singular values and omit the corresponding columns of V and corresponding rows of W star, we'll obtain a new matrix which has this property that it approximates the original matrix. This is the idea behind those two pictures earlier. So let's go back to those two pictures. But it only uses 100 out of the 769 singular values of the original matrix. They look identical. But the catch is, the one on the left, the original photo, takes about 6.30 megabytes. But the one on the right takes about 1.44 megabytes, representing a 77.22% savings in memory. So this proves useful in image compression problems. Now, in the next few slides, I'm gonna mention some of my works. We were able to show that they can be written in terms of other special matrices. The number of factors that you need in that decomposition depend on some quantity called the rank. The property of the matrix can be deduced based on that decomposition. And our related work is in so-called commutators of these special matrices. So another application of matrix decompositions is in principal component analysis. For instance, consider the classic data set of 3 species of a flower called iris, features of a flower. So the idea here is, let's say you have a new sample and you want to identify what species of flower that is. You can feed in that new sample, including the original data set, feed it to the principal component analysis. And principal component analysis will try to identify what species of flower that is based on that original data set. One of the key steps in principal component analysis is finding a unit vector x and such that it satisfies this equation where lambda is as large as possible. In math, this is an example of an eigenvalue-eigenvector equation. In general, unless the matrix A here has very special properties, computing eigenvalues and eigenvectors directly is very difficult. Hence, ways have been developed to approximate eigenvalues and eigenvectors. To the next object called the numerical range of a matrix. It's a collection of numbers of this form. The numerical radius is the radius of the largest circle centered at 0 that contains the numerical range. And one of the important properties of the numerical range is that it always contains the eigenvalues. Hence, if you have an idea what the numerical range is, then you have an idea or estimate for those eigenvalues. My work on eigenvalues 2 by 2 principal submatrices of normal matrices, where I fix the first eigenvalue and identify what are the possible locations of the second eigenvalue. In this picture, it's located in this blue region. And the description of the blue region depends only on the first fixed eigenvalue under certain conditions. And finally, my work on numerical ranges, three-joint numerical radius. It's a generalization of the numerical radius in the multivariable. The condition of the free joint numerical radius, this numerical condition, is equivalent to the existence of a positive definite solution. Was further characterized to be the main diagonal blocks that appears in a certain completion problem. So in math, because it allows us to view what was initially unrelated to something in a different context. In this case, this numerical condition was translated into a fixed point, the solution of a fixed point problem. As National Scientist Cruz said earlier, never stop reaching for the stars. So these players, there's still more work. So I have ongoing work at different stages with students. Some of them are BUSD scholars, with colleagues and collaborators outside the Institute of Mathematics. Thank you for your attention.
Dr. Dela Rosa. So for your questions, please reserve them for our open forum. Graduate of Master of Science in Chemistry from the University of Santo Tomas. She is an instructor in the Department of Chemistry at the University of Santo Tomas. Her presentation is entitled Anti-Proliferative and Cytotoxic Cytokalases from Sparticola. Okay, it's a very difficult.